Okay, we'll get started. The attendance poll is running, so respond to that. And let's see. All right, and we'll take a look. All right, let me have you guys settle down, please. Okay. Before we get started, I thought we would do just turn to your neighbor and discuss gradient descent. Okay. So it starts off. It says we're trying to find the values of w that minimize the function f of w. So w is some kind of vector, right? Gradient descent's an iterative algorithm. And so if we begin at some arbitrary starting location, say w at time 0, how do we select our next location, w at time 1? Okay? Go ahead and, I don't know, discuss amongst yourselves how we go about doing this. Okay, so does anyone want to say what we do next? So we're currently at w at time 0. We have a current location w, so what do we do? Yes, so we calculate the gradient at that location. Okay, we calculate the gradient at that location, and then and we just take our current location and we subtract off basically nabla, or the gradient at that location. We multiply it by some scaling factor, gamma, so that we don't take too big of a step or too small of a step. And this learning rate, this might be a difficult thing to establish, that maybe you have to just do some trial and error to figure out. But this is what we'll use, okay? And so today I'm going to introduce neural networks, okay? And neural networks, they sound fancy and whatever, and it's true. You can do all sorts of really cool stuff with them, and they can get as complicated as you want to make them. Much like linear regression, right? With linear regression, the base concept is simple, and then you can keep adding stuff to make it a lot more complicated. And similarly, we'll just start off with kind of the most basic version of a neural network, okay? And then like linear regression, you can take an entire course on neural networks. You can devote your life dedicated to researching and advancing neural networks. I have these two playlists, and I want to say both of them are required viewing, but I don't know if I say that. I don't know if you guys will watch everything. So definitely the Welch Labs one is going to be required viewing, okay? And then like almost required viewing, and there's not going to be like I won't spy on your computer to see if you watch these things or anything, but definitely they're both very good. I think this one's, they're about maybe an hour total in viewing time. So maybe about 2 hours total, okay? But I think they do a really, really, really good job kind of introducing us to neural networks. So watch both of these, please. Actually, my lectures are, kind of follow an example that was created by this Welch Labs, Stephen Welch made. Okay. And then again, just a disclaimer before we get into neural networks today, is that we are going to just explore the simplest kind of a neural network, okay? Like kind of the fully connected neural network with one hidden layer. That's about as simple as we can possibly make it. But you'll see it still does a good job. Neural networks have been around since like the 70s or 80s, but they've gained a lot of popularity in recent years because of kind of our computational advances. Like our computers today can do tons of calculations, especially with kind of these optimized GPUs that handle these kind of matrix multiplication very rapidly. They've developed neural networks and made all sorts of modifications and stuff to kind of handle different scenarios and different applications, and they power a lot of kind of AI technologies, especially image recognition ones. Okay, things that are able to now identify pictures. This used to be kind of like an impossible task, and now computers have gotten really, really, really good at it. To the point where we're designing self-driving vehicles and things like that. Okay. Again, in our class, we're just going to look at the simplest kind, this isn't like a neural network class, and it's not in the textbook, but I just thought it's a really cool application of gradient descent. Okay, so this is kind of my excuse for getting to play with neural networks, is that we use gradient descent as part of it. Okay. All right. So what is a neural network? Okay. A neural network is just it's the kind of a framework or a design for setting up a function. Okay. It's going to take an input and it produces an output. And that's basically what a function does. It takes an input and it produces an output. Okay. In linear regression, you've got a function that takes some inputs, and then it's called linear regression because it combines them in a linear fashion. It multiplies each of those inputs by a term, and it adds them together in a linear way, and it produces an output. Okay. And then a neural network, same idea. You take inputs, it's going to produce some kind of output. Okay. But the way it combines these terms is different from linear regression, and its inspiration comes from the brain. Okay, and so we still don't have a full understanding of the brain. We understand a lot of how these little components work individually, but then how they work collectively together and create consciousness and maybe free will. We're not quite sure. That's still being studied, right? And so, but anyway, in your brain, you've got billions of neurons, and each of these neurons are connected to thousands of other neurons via synapses. Okay, and in your brain, a neuron will receive a signal, and then depending on the signal and kind of the function of that neuron, and whatever, it might send a pulse or an action potential to other neurons, and then those neurons, again, they receive that signal, and depending on the signal they receive, they might send another action potential, and that's basically how our brains work at the most basic level, right? And then somehow, maybe, I don't know, they work together and we have thoughts and ideas, or maybe it's an illusion, I don't know. And so similarly, with an artificial neural network, which is what we're going to be creating, we create these things called nodes, okay? And then the nodes receive these input values, and depending on the input value, and the node will have an activation function. The node will send out a new value, okay? And that new value will go to other nodes, okay? And it's usually these nodes are kind of connected in these this layer-like fashion, so that one node will receive a signal, and then it will send it out to a bunch of other nodes. Okay, and so, yeah, so there are similarities between a neural network and maybe the brain, but the brain's much more complicated, okay? So don't look at this and think you can be a neuroscientist or something like that, all right? Okay, so anyway, I'm going to follow an example that was used in the Welch Labs video, okay? And the input matrix X will have two columns, okay? And he uses the example, hours of sleep and hours spent studying, okay? So how much sleep did you get? How many hours did you spend studying? And then our output is how well you scored on the exam. Obviously, this is how you score on an exam is much more, depends on more things than just how many hours of sleep you got and how many hours you spent studying, probably just which subject you're working on and who's your teacher and things like that. But we'll just keep it simple. And it basically you got two columns of X, and then you've got one output Y, all right? And so our training data will have n rows, and in our case we've got 3 rows, okay? And our X has 2 columns, or Y has 1 column. Okay, so this is where we start. Okay, and so all neural networks start with an input layer, and they end with an output layer. Okay, because that's basically how the function goes. You got the input. The first layer is called the input, and then the last layer will be called the output layer. And so we have 2 variables, or 2 columns in our input matrix X. So our input layer will have 2 nodes. Okay, when we draw our network, we're going to have 2 nodes in our input layer, 1 for each variable. Okay, so if you have 20, if your matrix X has 20 columns, you're going to have 20 input nodes. If your matrix X has, 800 columns, then you'll have 800 input nodes, okay? And so for things like an image, if you have an image that's 100 pixels by 100 pixels, and you want to do some kind of image recognition on that, your input layer will have 100 by 100, 10,000 nodes in its input layer, okay? Because you've got 10,000 columns. If you treat every pixel in your 100 by 100 image as an input, it's going to have 10,000 values of input, and so your input layer will have 10,000 nodes. Okay, and that's a tiny image, right? 100 by 100. That's like that's pretty small, and so you can imagine these networks getting quite big. Okay, but we're keeping it simple. We've got 2 columns in our input layer, 2 nodes, just one node for each variable. Okay. The output, in our case, is a single numeric output, the exam score, and so we're just going to have 1 node in the output layer. Okay. And then the network will have 1 or more hidden layers. Okay. So you've got the input layer, and then you have the output layer, and everything in between we'll call a hidden layer. Okay. And so for our simple example, we're going to have 1 hidden layer with 3 nodes in it, okay? this choice of having one layer and 3 nodes is pretty much arbitrary. It's just we're using small numbers to keep our introductory example simple. But you can have, thousands of nodes in your hidden layer, and you could have, hundreds of hidden layers if you want. Okay, so ours is going to be kind of the simplest that we can possibly make it. Here's our input. We have a hidden layer, and we have an output layer. Okay, and each node in each layer is connected to all the nodes in the next layer. This is what we would call a fully connected neural network. And so when we draw this, the diagram looks like this. Okay, we've got hours of sleep and hours of study. So your column x1 and x2. Our hidden layer has 3 nodes. So we've got 2 nodes in our input layer, 3 nodes in our hidden layer, and 1 node for our output layer. Okay, and each node is connected. So x1 goes to all 3 in the hidden layer, x2 goes to all 3 in the hidden layer, and each node in the hidden layer connects to the output layer, the node in the output layer. Okay, so this is what our simple neural network looks like. This is probably like as simple as we can make it, and it still counts as a neural network. Okay, where but yeah, in most modern applications, you've got thousands of nodes in each of these layers. Okay, you might have one node in the output layer. Maybe you could have thousands of nodes in your output layer as well, because you might be trying to predict, some kind of categorical thing. All right, can I flip to the next slide here? Okay. Okay. So just a side note. To talk about there's this idea of deep learning. Okay, so again, we had one hidden layer in our network that I just drew for you or showed you, but you can have say 100 layers. Okay, 100 of these hidden layers, and we might call that a deep neural network or a deep learning model. There's, I guess, other techniques fall under deep learning. So deep learning is kind of this umbrella thing. And you've got, but deep neural networks is probably the most popular thing in there. They've been shown to be incredibly powerful. So for example, there's a data set called ImageNet. It's got about 14 million images, and there's thousands of possible categories. And it'll be things like, this one is, it'll have things like, here's a balloon, and here's a mouse, and here's a rabbit. But it'll also say things like, this is a dog, but it'll be like, this is I don't know, Russell Terrier, and this dog is I don't know, some other kind of breed, and things like that. Okay, and so you've got millions of these images labeled with thousands of possible categorical labels, and for a long time, these networks, different models did not do a good job of identifying these things. But, in 2015, a deep convolutional neural network surpassed the human error rate. Okay, so if you give somebody this task, they're going to make some mistakes because it's hard to know the exact label of if you've got thousands of these categories and stuff. And so the computer surpassed this human error rate, and the performance continues to improve. I watched, followed some neural network lectures from Stanford last quarter, and they showed some applications. I just want to show you this one application, and this is powered by a neural network. But basically, it's the input is a video feed, and it breaks up that video feed into, well, here's an advertisement, but so it breaks up the video feed into pixels as its input, and it goes through and it identifies what it's seeing. Okay, so here it's correctly labeling which pixels belong to a vehicle, which pixels belong to street signs, which pixels belong to humans, I don't. Okay. This is. I wonder. I don't know why I'm being targeted for these ads. But I was blown away by its ability to recognize this is a car and that's a bus and these are people. And as it's moving along, it recognizes each of these objects. Here's a person on a bike and a thing. So anyway, this is powered by a neural network. Okay, we're not going to get anywhere near anything approaching that. But if you were to go to a grad program and study neural networks, you might encounter this. I have to warn you though, we were trying to follow along these Stanford lectures. I followed along with a few other students, and it was hard. The math and the coding was really hard. So it was a humbling experience, but very learning. Okay, one thing about neural networks is that they're really good at kind of this predictive performance. Right? You got inputs, you got outputs. And you can get your neural network to match your outputs very well, and if you give it, new test cases, you can have it perform very well in the test cases. Okay, but neural networks are not good for interpretability. So in linear regression, you get nice coefficients that carry some kind of meaning, right? It's like if you change x by this, it's going to have this much input out, this much. Effect on the output y, okay? And you have that with linear regression. You don't have that with neural networks. You're going to have these nodes in neural networks, and you'll see kind of the coefficients and the values going into the node, but you're not quite sure what this node is doing, okay? And I heard speculation that like we have neuroscience right now, there might become a new field of study which will be like AI neuroscience for figuring out what these nodes and neural networks do and stuff. Because it's just complicated. We don't quite know. You got thousands of these things, and they get trained. So anyway, here's our network again, and what I'm going to do is we're going to start turning this into math, right? So in our neural network, yes, question?
So it's like neural nets are used when there's a lot of application for like image processing or video data.
Mm-hmm.
Are there other types of data that neural networks are being used on a lot, or is it mostly for?
Yeah. So the question is, what are other applications of neural networks other than image data? And I don't know, I'm just telling you stuff that I saw in the class. So one thing they did was they took text input, okay? So here, one was they took images as input, and then they requested the output to be like a sentence, and to try to like caption the image based on what it saw. Which I thought was neat. And then other things was they took input, like they fed in like textbooks or like poetry, and then they asked the network to try to generate new poetry or a new textbook and things like that. And it had surprising results that looked like it could fool somebody into believing that it was real poetry and real like a real math textbook and things like that. It was quite impressive. Okay. I don't know if that answers your question. There's also, there's like new emerging fields like digital humanities, which is like now we're applying these statistical techniques to data from the humanities, which has generally, been less data focused, okay, and less mathematical. And and now you have these crossovers, things with kind of communications and stuff like that as well. We have a new faculty member who's 50% cross-listed with the communications department and the statistics department, because his analysis is I'm kind of not quite sure, but something complicated related to communications related data in terms of like language and stuff. And I think we have a linguistics and CS department now, and things like that. So all sorts of stuff are developing, and neural networks are used in a lot of these places. Okay. So anyway, in our neural network, if we look at this from layer 1 to our hidden layer, our input layer to our hidden layer, if we look at the arrows, we've got 6 arrows. Okay, we've got 6 arrows going from the input layer to the hidden layer, and we've got 3 arrows going from the hidden layer to the output layer. So we've got 6 connections in kind of our first 6 set of connections and 6 connections in our first set and 3 connections in our second set. Okay, each of these things are going to be have an associated weight, which loosely informs us like how important is hours of sleep to this node versus hours of study to this node. It's a weird concept, but like some of the nodes in your brain are important for hearing, and other nodes are important for vision and emotions and stuff. Each of these connections will have a different weight, and the idea of training our model is figuring out the weights of these connections. Okay, so I'm going to label all of these different weights. Okay, and I tried my best to kind of make it clear, and so here. The 2 weights that feed into the first node in our hidden layer, which I've labeled my hidden layer Z. So the first node in the hidden layer is Z sub 1, okay? And there's a superscript 2 to kind of indicate that it's like our second layer, okay? The weights that connect X1 and X2 to Z1 I've colored in blue, and that's W11 and W21, okay? So W1 goes from the first node to the first node, and W21 goes from the second node to the first node, okay? Over here, I've got W12, which goes from the first node X1 to the second node Z2, and here I've got W22, which goes from the first node X2 to this node Z2. And then here I've got W13, which goes from the first node to the third node, and W23, which goes from the second node to the third node, okay? These are all W's, and they have a superscript 1 to indicate that they are in the first weight matrix. And over here I've got 1, 1, 2, 1, and 3, 1 from each of these nodes going to our output node, which we're going to call Z3. And they all have a superscript 2 to indicate that they are in our second weight matrix. All right. Is that okay? All of these labels. So I've just labeled all 9 of these connections with different W's with different subscripts. Okay. And so W1 is the weight matrix from the first layer X to the hidden layer. It's got 2 rows. 1 for each node in layer 1, or the input, and 3 columns, 1 for each node in the output, in the layer 2, okay? W2 is the weight matrix for the second layer to the output layer, so it's going to have 3 rows, okay? So W1 goes from here to here, so it's going to have 2 coming in and 3 going out. So that's why it has 2 rows and 3 columns. And W2 goes from this middle to the last one, so it's going to have 3 coming in and 1 going out, okay? So we got 3 rows and 1 column. So I tried to color my letters accordingly. This was such a pain to do in LaTeX, but I pulled it off, and I tried to check for typos, but it's like so hard after your eyes get blurry. So anyway, this is I think this is correct. Okay. To kind of indicate going from the first x row 1 to this and this. Okay. So then when we multiply x times w, this is what we're going to get. Okay. X has n rows in it, but 2 columns. Okay. And W has 2 rows and 3 columns, so when I multiply those two together, I'm going to get n rows and 3 columns, okay? And so this is z raised to the 2, or not raised to the 2, z with superscript 2 to indicate this is kind of our second layer, okay? And so this is what I've got, okay? So when you multiply x11, when you do matrix multiplication, you do this times this plus this times this, and that's going to be what you have in this first corner. And then you'll do the next one, this one times this one, and this one times this one, and that forms the next value, and so on and so forth. And so when you multiply these, you're going to get 3 values for, observation 1, 3 values for observation 2, so on and so forth until observation n. So you're going to have each observation will have 3 values associated with it. So this is your Z matrix. Okay. Is that all right? You can probably just write this in your notes and just remember what these things are. Okay. All right, so after we produce our matrix Z, we're going to apply an activation function to every element in Z. Okay? So if Z is n by 3, we apply some kind of function to it. Okay, we do it element-wise, and so the result is going to will be n by 3. Okay, applying the function is not going to change the dimensions of the thing because we're just applying a function to each element individually. So if our matrix is n by 3, and just to indicate that that we've applied the function to it, we're going to call it A to kind of say this is what's been activated after our activation function. This is what we have. It's still at our second layer, so we have a superscript of 2 here, okay? And so for our class, we're going to use what's called the sigmoid, or otherwise known as the logistic activation function. And basically what it does is it squishes values between negative infinity and positive infinity to the range 0 and 1, okay? So when t is negative infinity, okay, e to the negative t is e to the infinity, so this denominator becomes infinity, and you have 1 over infinity. When t is positive infinity, this becomes e to the negative infinity, or this becomes 0, and you get 1 over 1. Okay, and so at extreme values, it goes from 0 to 1, and this is kind of what the graph looks like. At 0, it's at 0.5, and as you get further away, it kind of flattens out. Okay, and so this is our sigmoid activation function. I have to be honest, and the sigmoid activation function has fallen out of favor in recent years. Most neural networks today seem to use what's called a rectified linear unit, a ReLU function, or you can have like a hyperbolic tangent or a leaky ReLU, and there's all sorts of stuff you can. There's a Wikipedia article on activation functions alone, and there's like a huge table of these things. We're gonna just stick to the sigmoid. One is because it's used in both of these video series that have been produced. And 2, it's differentiable everywhere, which can't be said about everything else. And it was popular historically, so I think it's okay that we're kind of going old school on these things. Okay. So again, here is our thing, and so we've left off at applying the function z2 onto z2 and getting a2. Okay, I don't have a2 labeled here, but basically after applying a2, that's going to be kind of the output of each of these nodes. Okay, and so we're going to take a2 and multiply them by w's and combine them to get our output z3. Okay, so I've got a2, and I multiply it by w, which is 3 by 1, and we get z, which is going to be n by 1. So a is n by 3. That's kind of the result of applying the function. So I've got all of this stuff, and then we multiply it by w. And when we do that, we're going to get an n by 1. Okay, so we've got one output for each input. So each observation has 2 input values, and then they kind of go through a network and it produces one output value, which is what we want. Okay, but it's done it by kind of combining them like this. Okay, and then our last thing after we do that is we just apply the activation function again to this thing. Okay, and we'll just continue to stick with using the sigmoid activation function on this last thing. Okay, there's no rule against using a different activation function at these different layers and stuff, but for simplicity, we'll just use the same activation function on the hidden layer and the same activation function for the output layer. Okay, and after we apply the activation function to our output layer, that will form our estimate y hat. Okay, so in summary, this is what we've done. We've taken our input x, we multiplied it by our first weight matrix, and we get this. We apply a function to z to get our activated values, our activations. We multiply our activations by a second weight matrix to get another set of z's, okay? And we apply a function there, our activation function there, and we get our output y hat, okay? And so if you just kind of combine them all, you get y hat is equal to f of x times w times w2, okay? So it's just a function, okay? We illustrate it, you know, kind of with the neural network to show kind of all of the interdependencies between these things and the interconnectedness, but at the most basic level, it's a function. You take inputs, you do some stuff to it, and it produces an output. Okay, and so this is what we have here. I do feel like I need to talk about bias terms. So this is what, if you watch the Welch Labs video series, which you need to do, okay? It's gonna do this, all right? And I tried to follow the same notation that the Welch Labs videos did, so you can kind of follow along in his videos and my lectures and not get too confused. But for whatever reason, he didn't use bias terms, okay? And so, you know, a bias term just adds a constant at each node before applying the activation function. So it's just like adding an intercept to linear regression. And so I've kind of illustrated what this would look like. Each node will have its own bias term. Okay, so you've got B1 and B2 and B3, one for each of these nodes, and then we would also have a bias term for our output node. Okay, and they just basically you're going to do x times w plus B1 to make kind of your z. All right, so there's going to be one bias term. Okay, so our matrix of biases, kind of for our first one, is going to be 3 by 1. Okay, we're going to have, there's only one bias term for each thing, and so in order for the dimensionality to work, I have to kind of duplicate our biases so that we're going to add the same set of biases for every observation. Okay, so I just have to multiply the biases by a matrix of ones, okay? And I'm not quite sure why, but there seems to be a general consensus of calling the ones J, a ones matrix J. So so anyway, this is what we've got, okay? So like before, x is n by 2 and w is 2 by 3, and so this will form an n by 3. Our bias is 3 by 1, so I transpose that, okay? And then I'm going to multiply that by j, which will be n by 1, and that's going to also form an n by 3 matrix. Okay, and then now I can add those two together. Okay, so here I've got this. When I do this, this is going to form an n by 3, and then I do basically a column of ones. Okay, And when I do this by B transpose, okay, you're going to get an n by 3 matrix, and then you can add this. Okay, and so this will add B1 to everything in the first, kind of going to the first column, first node. So the first node will all get B1s, the second node will all get B2s, and the third node will all get B3s. This green is harsh on the eyes, but I don't have a better color. Okay, so so this is what we've got. Okay, we do a similar thing for the output thing. I technically don't need to transpose this, but just for consistency, I've transposed it. Okay, and so you've got this. Okay, n by 3 coming in. Times 3 by 1 W, and then J is n by 1, and B is 1 by 1, and so when we do that, we're just adding a constant term to all of this, and we're going to get an n by 1 output as well. There. Is that okay? Okay, and so kind of the summary here is we do, xw plus basically just b, 1 times b, to get our z's. Okay, we activate those, and then we apply, we multiply that by w, and then we add our bias terms, and we get another set of z, and we apply the activation function there, and we get our y hats. Okay, so this is just what it looks like, and that's what you go. Okay. And so, okay, so now we're at a place where we have y hat values, and we're going to throw our y hats into our loss function, okay? Because the ultimate goal is to be able to train our network, and in order to evaluate how well our network is performing is we need to evaluate a loss, okay? So we're going to run our inputs through and see what it predicts, and we're going to compare what it predicts y hat versus the actual value, okay? And then we're going to take the difference between that and square it, and we'll get kind of our sum of squared errors. And so this is what we have, and so we've got this, or if you use biases, it's going to look like this. And so what we'll do in our next class is we are going to differentiate the loss function with respect to our weight matrix W1 and our weight matrix W2, and also, I guess, well, maybe in your homework I'll make you do it with respect to the bias terms, so that we can start training. Yes, a question before we go.
What is the bias term? Like, what's the purpose of the bias term?
What's the term of the bias? Yeah. What's the purpose? It's just adding a constant, okay? So you you multiply your x times your w, and then you're just you're adding it. So it's basically like including an intercept term into your model. Okay, so it's adding a constant to everything. So it's just one more term that you can use to adjust. Okay, we'll end there. We'll see you guys on Friday.